Monthly space news. That is everything that happened in the last month, about 30 days before this. That's another one of those shots from the Orion capsule for the Artemis mission. Far, far away at the far point where you can see the moon in the foreground there and the Earth kind of more in the background. So the highlights of this last month. First of all, of course, is the Artemis launch itself to lunar orbit and the return coming tomorrow. There's a lot of jargon that gets thrown around when people talk about this mission and any other for that matter. So I thought I'd actually talk a little bit about the Oberth effect and gravity assist, slingshots and those kind of things. Actually, all those things are involved in this mission. It wasn't obvious at first until you started looking at what they really did. There was a lunar launch delay, totally independent lunar mission on a Falcon 9 that got delayed. We had talked about it briefly last month, and it's going to be delayed. I'll talk a little bit about some construction 3D printing to build roads and habitats and so on the moon and Mars. There was a small scale funding for that was going on by NASA right now. Related to that, there was a Mars analog, meaning kind of a simulated Mars and space station that was actually being done at Johnson Space Center. I should give you an update on that. One thing we talked about last month was that there's this project called the NEO Surveyor, a space telescope to look for killer asteroids. And it had been requested for quite a while by Congress in a couple of places, and it's finally gotten revived and it's back and going again. And then we'll talk a little bit about some of the recent launches to space. Okay, the big one, of course, is Artemis 1. That's the Space Launch System as the rocket, Orion as the capsule. It's basically a big test. There's no people on this. And you're testing out the rocket itself, which is really the first launch for it completely. The Orion spacecraft had been tested before, but it's never been tested coming back from the moon, which is at a much higher speed. And so the big question there is, will it survive? It has a heat shield, and they've modified the heat shields. Some of the same materials, but they changed the way they put them in there. So that's going to be the big question. This 25-day mission, no crew, orbiting the moon, returning tomorrow. And along the way, they deployed 10 small satellites. I'll talk about those next time because there was a lot of uncertainty as to how many of those actually survived. They've been sitting around for so long because of all the delays, the batteries had run down. It wasn't quite clear what was going to happen to all of them. So we'll talk about that next time. Artemis 2, it says here it'll follow a similar path. It's not quite the same path. But Artemis 2 will be going out to the moon and back, but it's basically just going to be one shot around the moon and back. And scheduled originally for 2024, it may well slip to 2025, not clear. So we have to wait a couple of years at least for the next one. But anyway, at this point, SLS is the world's most powerful operational rocket. Before that, it was actually the Falcon Heavy, even as of last month. But now that this is finally proven that it works, it is the most powerful. Just for some comparisons, we put the thrust in here, 8.8 billion pounds. Falcon Heavy is at 5. But in past rockets, the shuttle and the Apollo were a little bit smaller. But of course, when Starship, assuming it eventually does fly, that'll actually be almost twice as powerful in terms of thrust. We've shown some of this stuff before, so I'm not going to spend too much time on it. But on the left-hand side here, you see what the rocket looks like with, this is the whole thing, what it looks like when it's going up. It's got the solid boosters before they drop off. It's got up in the upper stages, it has the Orion capsule, which really includes two parts. There's the capsule itself, that's the only part that actually gets returned to Earth. And then there's the service module, which is put together by the European Space Agency. And that contains propulsion and life support. So that gets jettisoned right before they finally re-enter the atmosphere. They jettison even most of their life support because it's a very short ride down at that point. Very terrifying ride, but very short. So one thing you don't see is what connects the Orion capsule to the rest of the SLS rocket. In between, there is a thing called the interim cryogenic propulsion stage. It's basically an upper stage. It actually provides a lot of propulsion once you get out of low Earth orbit. And then it gets abandoned and actually it gets shot off into an orbit around the sun at the very end of it. So this is that picture that I showed you in the beginning again. This is taken from Orion, and that's certainly not something you see every day. That did set a record. The Orion has gone the farthest from Earth for any human-rated craft so far. It went about 270,000 miles out. That's on the far side of the moon. The Earth, moon is on the other side of the moon, way past that. The previous record was 248,000. So it did beat it, not massively, but it definitely did beat it. The orbits that they're in, the one main orbit around the moon that was used here is called a Distant Retrograde Orbit, which an awful lot of people hadn't heard of, until this particular mission. The distant part means that it really goes far away from the moon, but how far? It's far enough that it goes beyond the Lagrange points with the Earth moon. And what that means is those are points where force is basically balanced between Earth and the moon. And there's a couple of those. There's one in between the moon and Earth and one on the other side of the moon. As long as it basically goes outside of it, it turns out that makes it very, very stable because that orbit is really influenced by both the Earth and the moon. So it's a very, very stable orbit. Now, this would have been used in the past. An earlier version of the Space Launch System, originally under the Obama administration, it was going to go and capture an asteroid and bring it back. And they needed a place to put it. So they're going to put it in an orbit around the moon, which sounds like a pretty dangerous thing. If you screw it up, a big asteroid crashed into Earth. But anyway, obviously, one, that didn't happen, but two, this would have been a very stable orbit to put it in. It does change slowly over time, but it's very, very stable, much more so than almost any other orbit. And that's why they used it. One of the reasons they used it in this mission is that if anything did get screwed up and you had a time to fix it, some kind of loading software or something, because it would go around in the same orbit, you had several shots to fix it quick. So that's one of the reasons they favored that. So it would have been used back in capturing an asteroid, but that didn't happen. The actual first use of it was by the Chinese. They had a lunar orbiter, and they put one in it, and that was only the beginning of this year, so it wasn't even that long ago. The theory behind it had been developed, years and years ago. Everybody knew about it, but nobody had ever actually done one, and now they have done one. So it's called a distant retrograde orbit. We talked about the distant part. The retrograde, that's a word that's used in astronomy, rocketry, and it depends completely on context what that actually means. If you're talking about an object by itself, like a rocket or a satellite, retrograde, if you would do a retrograde burn, meaning you burn some fuel to change your orbit, that means it's just in the opposite direction. It has retro rockets and all that. It just means you're going this way, so that at least the main component of your thrust is in the opposite direction of what you're going. So that's one use of retrograde. Another one, though, if you're talking about an object around the planet, then retrograde orbit is in the opposite direction of the planet's spin. So, for instance, if you're launching a satellite, you care about whether it's a retrograde or prograde, the opposite, because you got the Earth's spin working for you. And if you launch, especially the closer you are to the equator, if you launch at the equator by the Earth's spin, you're already moving about 1,000 miles per hour. That gives you a lot of kinetic energy. You want to add to that speed by launching to the east, the prograde direction, not the other way, which would be the retrograde direction. If you're launching to a polar orbit, one that is passing over the poles, then that wouldn't be a benefit. But the point is, launching in the prograde or retrograde action has a big impact on the cost to orbit for many launches. But now there's another case where you're talking about a planet and a moon, and you're looking at that combination system. Then, if you talk about an object orbiting the moon, then the orbit is a retrograde if it spins in the opposite direction of the moon's orbit around the Earth. That's clearest when the object orbit is in the same plane as the moon's orbit around the Earth. Then from where you're standing, if the moon rotates counterclockwise around the Earth, then a retrograde moon orbit would rotate clockwise. In this diagram of the overall Artemis mission, the moon is orbiting the Earth in a counterclockwise direction. The gray circle to the right, around the moon, is the distant retrograde orbit. The Orion capsule enters that orbit at the point marked number 10. It enters that orbit going clockwise. It only goes half an orbit to point 12 where it leaves that orbit, but without the burn at point 12, it would continue orbiting in the gray circle for a long time. Let's talk about the overall mission. The rocket was launched, and the outbound path is shown in green here. The solid rocket boosters and then the core main stage all dropped off. The interim cryogenic propulsion stage, the ICPS, it did a burn to head for the moon at point 5. After that, the mission split in two. Orion ejected from the ICPS and coasted towards the moon. The ICPS dropped off the 10 secondary satellites at various positions, shown as A, B, C on this diagram, and they also coasted toward the moon. And as both the Orion and the ICPS coasted toward the moon, they slowed down due to the constant pull of Earth's gravity. That's just like throwing a stone up in the air. The stone slows down while it's rising. As both craft approached the moon, however, they also got pulled more by the moon's gravity. We'll cover the details later. That's where we're getting into the Oberth effect and in gravity assists. In general, the idea was to get Orion into the distant retrograde orbit, which is the gray circle. The goal for the ICPS was disposal, just get it out of the way by putting it into an orbit around the sun, escaping the gravity of both the Earth and the moon. Some of the small satellites were also headed for solar orbit. Others were headed for lunar orbits or lunar landing. They generally had their own power, so they could control their own path.
Orion's maneuvers near the moon relied heavily on the Oberth effect.
The basic idea is you're changing orbits. You're going from one to another. It turns out there's a question to ask. When should I use the thrusters on my rocket? When should I burn? Do I do it when I'm up high? Well, it turns out you want to do it as close to the moon as you possibly can. You actually get a bigger kick that way, which is not really completely intuitive until you look at it more carefully. And the reason is it really all comes down to that graph right here, which I'll explain in a second.
Basically, it's all related to kinetic energy. Kinetic energy is the energy associated with motion. Kinetic energy increases with faster motion and with heavier mass. It is proportional to the mass and proportional to the square of the velocity. So for a given mass, this graph plots the velocity of an object on the horizontal axis and the kinetic energy on the vertical axis. Now, imagine a rocket is coasting at some velocity v. From this graph, you could read off the kinetic energy. Now, if you burn some fuel for a short time, you would get a burst of thrust expelling the propellant as gas at high speed. Now, that'll generate a fixed amount of thrust and hence a velocity change of delta v, independent of how fast the rocket is going. The Greek delta symbol in front of the velocity v just means a change in the velocity. So, how much effect does the burst of thrust and delta v have on the kinetic energy? Well, from the graph, you can see the effect of a given delta v on energy, shown as delta E. That same delta V results in a bigger change in energy the faster the rocket is going. It follows from the shape of the curve. The math is shown on the slide. You start off with some initial kinetic energy based on the formula of kinetic energy equaling 1/2 of mass times the velocity squared. After the short burn, the final velocity is v plus delta v, and then the final kinetic energy is shown. You subtract the initial kinetic energy from the final kinetic energy, and there's a term. Now that shows that the final kinetic energy depends on the velocity v, the initial velocity.
The faster you're going, the more energy you pick up. Now that's different than what's called a slingshot maneuver. That's just based on gravity. You hear that term a lot. And awful lot of the interplanetary probes that we've done, where they go from asteroid to planet to asteroid and so on, they all use this. And basically there, you're just saying, I'm going to go near some object that's moving around the sun really fast. And if I go anywhere near it, I'm going to get kind of pulled along. And the exact effects differ depending on the angle you come in. But fundamentally, you're grabbing, because it's pulling you, you're grabbing away some of that energy. So you get some energy for free. It balances out because you're actually stealing it from the bigger object. But the bigger object is so big, it doesn't notice the difference. You're the small thing like the rocket, and it affects you. So anyway, now this interim cryogenic propulsion system, the upper stage of SLS, uses that in particular. And I'll show you that on the graph when we get to it. But does this really make sense? Most people have trouble kind of getting their head around that because they think, well, okay, we're burning some fuel. There's a certain amount of chemical energy we're getting out of that, and we're using that to blast out the exhaust. How could it possibly make a difference how fast the rocket's going? Well, the way to think about it is, if you are in your rocket, you've got a lot of propellant, which is usually most of the weight of the rocket. That propellant itself has kinetic energy. It's moving along with you. So you're starting off, your initial condition, you're moving along. You've got a bunch of fuel that has its own kinetic energy as well as the chemical energy. When you blow it out the back, then what happens is some of that energy is obviously taken away. The question is how much of that actually transfers to the rocket. And that's where the whole thing is. So think of in some extreme cases. I mean, for instance, if you're sitting on the launch pad and your rocket is just running its engines, but maybe it's still held down by some straps or something. Basically, none of that energy of that burn goes into raising. It doesn't change the velocity of the rocket at all. So that's one extreme case. The other extreme case is suppose you're going along, and the easiest way to think about a lot of these kind of issues with rocket thrust is don't think of it as shooting out gas. Think of it as shooting out
marbles.
Those marbles have velocity. They had energy. Some of them got dropped off. And if you actually drop them off at exactly the speed you're going, those marbles end up sitting there at 0 speed and the rocket goes on. Well, energy is always conserved. So if there's no more energy at 0 velocity, there's no kinetic energy in those balls. There are transferred to the rocket. And that's why the whole thing works. So where does this get used in Artemis? Multiple places. Let's just follow the path of Artemis. It's launched from the Earth. It's going through these green numbers here as we split off for the small satellites. And actually, let's look at the small satellites first. That one, there's some vinyl burn here. The small satellites get dropped off. And this thing just kind of comes around. And what happens is during this period, you're just getting further and further away from Earth. So, it's like anything else that's going up, it slows down. So it's slowing down, being pulled constantly by the gravity. Eventually, it gets really close to the moon and it starts to get sucked in, then it starts to go faster. Now, for this propulsion stage, it doesn't do any additional burn at all. It just gets slung around. That's called the slingshot effect. But for the Orion capsule, they go ahead and they go down and they go charging toward the surface. But then they actually, when they get as close to the moon as they can, then they turn on their thrusters. They burn it really fast, and that shoots them out. Like it shoots them back up here. So that's kind of weird because, you're coming along, you're reaching about the point of the orbit. You think you just, expend some fuel here to go into this big orbit, but you don't. Actually, it's more efficient to drop down to the moon and pop back up. Anyway, once you're there, you're in this orbit, it's stable. You're already matching the moon in terms of your velocity on the average, it's going around the moon. So it's really obvious here, right? You get to point 12, this point on the map says, okay, we want to go back to Earth. So how do you go back to Earth? You might think you would just blast your way forward and head toward Earth. But no, actually, that is not the most efficient way to do it. The most efficient way is to slow down. So it's very counterintuitive, but you actually slow down at that point. You do a retrograde burn. You actually purposely slow yourself down. Then as a result, you tumble in toward the moon. And of course, you pick up speed when you do that. And you get swung around, and then you apply a burn. When you're in as close to the moon as you can, you blast your way out, and then you're back on your way. So they're really taking advantage of the odd physics, if you will. But it's kind of hard to do all this. They have a lot of computer programs to figure it out. They still do a lot of trial and error. But anyway, they come up with these orbits. Okay, totally different lunar launch.
A lot of times when missions get delayed, it's because the payload isn't ready. But in this case, there was some problem with the Falcon 9 rocket.
But two missions got held up. One called the Lunar Flashlight, talked about last month. Its purpose is to survey the water ice that's in the craters. The other thing is there's going to be a lander.
Our next topic is about construction. Long term, for sustainable presence on the moon or Mars, we need to be able to build using local materials. It's just too expensive to import building materials from Earth. NASA and the Air Force are funding research to use 3D printing for construction on the moon or Mars. This includes landing pads, blast shields, roads, and habitats. In the foreground of this illustration, you're looking at construction of a landing pad on the moon. This ensures a flat, stable surface for safely landing spacecraft, and also reduces the amount of dust thrown up during takeoffs and landings. This matters because lunar dust in particular is like tiny shards of glass, very tough on materials and people. The vision here uses autonomous robots. At the end of a robot arm, there's a laser or other equipment that melts regolith, the dirt, fusing it together to make what are essentially interlocking bricks. Other robots are shown building a road to the landing pad. Off in the distance, there are robots creating buildings or other structures. This illustration suggests that building roads on the moon has something in common with highway construction on Earth. Here we have more highway department employees standing around watching the work get done than people actually doing the work. NASA and the Air Force have awarded an SBIR Phase 3 contract to ICON, which is an Austin-based company that is already building houses on Earth using 3D printing. The contract is for $57 million. SBIR stands for Small Business Innovation Research, which is a form of funding long used by a lot of federal government agencies for research by small businesses. Typically, the funding for the phases starts small and then grows with subsequent phases. ICON previously 3D printed a structure called the Mars Dune Alpha at the Johnson Space Center. That's a Mars-based analog for simulating operations on a Mars station. The simulated Mars missions is called CHAPEA for Crew Health and Performance Exploration Analog. Anyway, the project that is now being funded as an SBIR will probably be based on laser sintering or some other technique involving melting of the regolith, rather than some form of cement like that used in 3D printing of houses or used in that Mars Dune Alpha project. This research is part of an overall NASA project called MMPACT, which stands for Moon to Mars Planetary Autonomous Construction Technology. It's going to include testing on the lunar surface using robotic landers, maybe in 2028. Interestingly, the Chinese have similar plans, including testing of 3D printing from a lunar lander in 2028. We reported on the Mars Dune Alpha project back in October 2021, so this seemed like a good time for a quick update on its status. The inset picture to the left of the slide is from the 2021 news story. The 3D printed habitat covers 1,700 square feet for use by a crew of 4 people. In its partially completed state, you can see the crew quarters and various other rooms. That's in the picture on the lower left side there. The 3D printer is on rails on the outside edges of the building, with the printing arm overhead between the rails. It's visible in the right corner of that lower left picture. The printing nozzle can be seen in the picture at the bottom center. The printing material is called lavacrete, which is Portland cement mixed with crushed lava. For this project, red dye was also added to make it seem more Martian. Water is used to make the lavacrete, just like it's used on Earth. The CHAPEA missions seem fairly conventional and similar to many other Mars analog missions. They're going to focus on physical operations, human behavior, and food systems. What is new is the 3D printing for the habitat. So, where does the project stand? The construction was completed in May of 2022. It was built inside of Building 220 at Johnson Space Center. The entire structure was not done using 3D printing. For instance, the roof was cast in pieces outside and put in place with cranes. Several papers have been published about this project. Many 3D printing issues for Mars or the Moon were identified and some were addressed, but few could be tested because conditions inside an air-conditioned building at atmospheric pressure don't match the severe environment of Mars or the Moon. Issues identified included one, integrating parts brought in from Earth, in particular, things like airlocks, windows, power lines, and so on. A major issue, of course, will be pressurization and sealing. These issues were considered, although not tested, in this project. Mars pressure is 1% of Earth's, and of course, the Moon is even less than that. They couldn't test for that. Thermal expansion and contraction would be a big concern in any of these projects. For instance, on Mars, maybe on a warm summer day at the equator, you might get 60 degrees, but then it could still drop down to 100 below at night, and maybe up to another 100 degrees lower at the poles. The Moon would be even worse, of course. They did test out building special joints to avoid cracks, and they knew that would be needed. So techniques for that were included in the building, but of course the testing of their impact wasn't really possible. It was also suggested that structural reinforcement would be helpful. Another issue, of course, would be vacuum and cold conditions during the construction, which they couldn't really reproduce. One issue not really considered is the chemicals that are actually in the regolith. Mars regolith in particular has poisonous perchlorates and all kinds of other differences from Portland cement. So there's issues of human health as well as what chemical reactions will actually occur. Another issue is the use of water. Of course, water was used for this concrete. It was basically Portland cement. Besides the likely difficulty in getting the water on Mars, there's also the issue that other studies had shown that rapid water evaporation under high vacuum could lead to very porous concrete, not really strong enough to be useful. In general, other work that has been done as part of this M-Impact NASA project had led to the conclusion that using water for construction on Mars or the Moon was pretty unlikely. The only possible chemical binder left in contention is one based on calcium, sulfur, and aluminum. Those weren't tested here, but that's been part of the other research by NASA. So instead, some form of laser sintering, or in general, some way of melting all or parts of the regolith would probably end up having to be used. The estimated mission start date has also slipped. It is now set for the summer of 2023.
Okay, one more of the missions. The NEO Surveyor, Near Earth Object Survey. Near Earth Object means things like asteroids and comets they're going to come within 30 million miles of Earth, and at least actually the definition is like 300 or 400 feet diameter, but they can detect them down to 100 if they use this telescope. Well, they had a big review point. They passed it on December 6th, saying that yeah, they're going to go ahead and build it. They kind of ignored doing it before this. They didn't really have funding. Congress ordered them to build it. back in 2005 and also in August. But they didn't really fund it. So, it's kind of hard for NASA to say, okay, I'm going to build it, but, I need money. So they finally look like they're going to get that. So, and of course, the cost has gone up. Now it's about 1.2 billion, but it would launch in June of 2028, current plan. Miscellaneous stuff. Chinese space station is up and running. For the first time, they sent up a second crew. They've had 3 people there. They sent up another crew of 3. So that means that for a while, there's an overlap crew where there's 6 there at once. They have enough in place they can support 6 people. And so they're doing that. So they're making progress on their space station. All right, that's it. Now we can talk about our usual item. How many launches do people think we've had? Meaning since the last meeting. It's about a month, roughly. And by launches, we mean launches to space. The suborbital ones don't count. It's really, you have to go to space to do that. One clue, of course, is, okay, we know about Artemis. That's the Artemis launch. It's right there. But how many others do people think we have? Any guesses? Okay, I heard of 6. That's definitely too low.
50.
Okay, too high. All right.
No, it's too high, but at least 20.
No, actually, in a lot of recent months, in fact, we've had, we had like 25, 26 or so. But now, actually, it turns out it does take a second page to get to it, but it's really only so that's a little less than we've been seeing. One thing that's interesting here is that typically every one of these months when I ask this question, there's usually at least 1 and probably up to 3 launches on a Falcon 9 of Starlink satellites for internet service, from SpaceX. Not one. The only one that's related to that is down here at the bottom. Yeah, there's a Falcon 9 that launched some communication satellites, but it wasn't for them. It's for their competitor, OneWeb. So the thing is, they pretty much have sewed up the medium lift launch business. When the Russians are out of the picture because of Ukraine, they're pretty much forced to go there. They had a lot of satellites up already. It just takes them up to 504 out of their 648 that they're aiming for. There's 3 missions coming on SpaceX, and there's another couple that they're using in the Indian space for that they have spare capacity. That's about it. Not much else to talk about this week here. And of course, we talked about Artemis, which really is the big one. Cargo resupplies. The Russians are still launching. They're typically, last time we noted they actually had a lot of launches. Most of them were their navigation satellites, the GPS equivalent. They finally finished off. They finished off the current constellation of that. That's really about it. So yeah, Chinese have they're always coming up with new rockets. They have a new one that's solid in this case, launched from a barge. So anyway, that's pretty much it. Any comments or questions? Okay, if not, we'll get to the main speaker, Andrew Paris. I pulled some of this off our description, but he can probably tell you all this himself. But he's been involved in space for a long time, supporting space shuttle, national space shuttle operations. Obviously, he's been on the same thing that Nathan's been on, and actually quite a few of our speakers that have taken this, where you experience weightlessness for the 3 minutes or whatever each time, or low gravity with the Mars. Anyway, you're going to hear about his personal view of our journey to the stars. So I'll turn it over to you here.